Before I start this video, let me take 30 seconds to tell you something about Exergic. Exergic is India's most trusted and most experienced institute for online GATE preparation. I am Chandresh Mahajan, founder and chief educator at Exergic. I am an All India rank 37 in GATE Mechanical Engineering, an ex-Indian Oil officer having 7+ years of teaching experience as of now. These are the GATE 2021 Mechanical Engineering toppers from Exergic. You can find their preparation strategy on Exergic's website. To know more about our GATE courses, you can visit our website or contact us on these details. Also, you can download Exergic GATE preparation app from Google Play Store. The link is available in the description of video. Now let us solve another problem, and this problem will make you even more comfortable in analyzing the load and deformation acting on a body. We know that stress strain diagram as well as load deformation diagram, both the diagrams are used to analyze any given situation of deformation. Obviously, stress strain diagram is most popular because of the reasons that we already know, right? So load deformation diagram or load deformation curve is not that popular because it can change with the dimension of the body. So it's not good when you want to, check for the properties of the material, right? But when you have a specific case, a specific loading, a specific dimension or body given to you, and then load is acting on that, then load deformation curve can also be used because the dimensions are not changing now, right? We are not trying to compare this body with some other body, or we are not trying to compare the property of this body with the property of some other body. In such a situation, load deformation curve are good to go, right? They are in fact used for such situations. From the point of view of GATE, obviously stress strain diagrams are more popular, but it does not mean that load deformation diagram is not in the syllabus or load deformation diagram cannot be asked. You should be comfortable with that. Even in some other subjects also, load deformation diagram has been asked previously in GATE. So this is something which is very relevant. But as you know that since we don't solve many questions from this, you may not be much comfortable. But after this question, you are going to get even more comfortable with load deformation diagram. Let us start the question. So the problem says that a rod and tube of 500 mm length are attached to a fixed support at one end and to a rigid plate at the other end. As you can see in the diagram here, a component mentioned as tube, other component is mentioned as rod. You can see that both of their lengths are equal and that length is 500 mm as given in the question. At one end it is attached to a fixed support and at the other end it is attached to a rigid plate, both of them. Okay. Now, what is the significance of rigid plate? Rigid body, we already know what it is, right? It's not going to deform, there will be no change in its shape or size. So, when we are going to load this total assembly, whatever will be the deflection of any one of them will be same as the deflection of the other one, because at one end it's a fixed support which cannot move anywhere, and at the other end there is a rigid plate, and rigid plate cannot bend or cannot get deformed. So it is not possible that tube will elongate more, rod will elongate less, and plate will get bent. It's not going to happen. So rigid plate is going to ensure that both of them deform with the same amount of length, with the same value. This is the significance of rigid plate. So whenever you get a question, whatever is the subjects, generally these design subjects, be very careful whenever you see rigid term. There are many such problems in thermal stresses also, where when one component is rigid, other is not rigid, it can change the situation. As we will keep on solving more questions in more subjects, this thing will get more and more clear to you. So up to this, the question is clear to us. Okay. Both tube and rod are elastic, perfectly plastic material. This type of material also, we know what it is, right? It is elastic, which is a linear line. It's going to be a linear line from Hooke's law, and then it will be perfectly plastic, right? There are different names to refer this. You can say perfectly elastoplastic material, you can say linearly elastic, perfectly plastic. All these names refer to the same type of material having the same variation, where there will be an elastic region and then a perfectly plastic region, right? We have discussed this already. One point I would like to add here, for the sake of this question, I have shown rod and tube like this, like rod is below the tube, right? Something like this. Practically, this is not how it will be, right? Practically, rod will be inside the tube if you have a rod and tube assembly in the question, because tube is hollow, rod is solid. So when they are assembled together in any general question, if nothing separate or nothing exceptional is mentioned, the rod will be inside of the tube. Tube is hollow, rod will be a solid one inside the tube. Tube will enclose the rod. In this case, in this question, it is not going to matter. So for the sake of simplicity, I have shown both of them like this. Okay. So these are the properties of the materials of rod and tube and their dimensions that are given to us. Area, which is cross-sectional area. Okay. For rod is given in centimeter square, for tube also it is given. This is Young's modulus given for both. This is yield strength given for both. So these values are known to us. Let's now read what question is actually asking us. There are two parts of the question. First is asking you to draw the load deformation diagram for rod as well as for the tube. Now you may think that, sir, GATE is not going to ask such question that draw it, because GATE is not a subjective paper. But please remember that whenever we are going to solve questions, especially solved problems in the course, they are going to be such problems which will involve questions which are slightly higher in difficulty level than GATE, because these are not meant for your practice, these are meant for learning. Whatever I am going to tell, in different solved examples I am telling you, is meant for learning. So many things you will learn new in these solved examples, which are, generally not covered and taught anywhere in the theory. So be ready for this, that you will have some questions which will be slightly subjective type, right? But let me be very clear that GATE can ask such questions also. Easily such question can be made. 4 options will be given. Each of them will be having a different load deformation diagram. So it's not that question cannot be asked like this. The question that we are going to discuss right now, it is going to be slightly lengthy, but sub parts of this question can be definitely asked directly in GATE. There are 4 or 5 different small questions can be made from this one question that are very much probable and good for concept building also. Okay. So first part is asking you to draw the load deformation diagram for both of them, and it is also asking you to determine the net deformation in mm. Net deformation means this net deformation of this assembly, of this rod and tube assembly. When a load of 11 meganewton is gradually applied, when 11 meganewtons load is gradually applied, how much is going to be the net deformation of this? Okay, this is first part of the question. Second part of the question we will come to when we complete the first part. Second part of the question you will find more interesting once we are done with the first part of the question. So let's not look at the second part as of now, but it is interesting and more important than the first part. Alright, so the first part of the question is asking to find us the load deformation diagram or load deformation curve for rod and plate. Now in a load deformation curve, what exactly do we have? We have an axis of load, which is P, other axis of deformation or deflection, which is del, right? So these two values we need to find out at critical points so that we can draw the curve of this, right? What are some critical points? In this question, the yield strength is the critical point, the yield strength, right? That point has been mentioned, and since this is an elastic, perfectly plastic material, so it is going to be something like this and then like this. This zone is going to be the elastic region, this is going to be the plastic region, and since it is a elastic and perfectly plastic material, this line will be horizontal. This is the point which is showing you the yield strength, right? So if you find out the value of yield strength and you find out the value, it's not sigma actually because it is P del curve, but if you find out load at yield strength and then you find out the deflection at yield strength, you will be able to join this and make a horizontal line and get the load deformation curve, right or not? So whenever there is a discussion about load deformation curve, you have to draw one or you have to find out the right one. These are the critical points which will matter. So you need to find out the load at yield strength, how much load will be required to yield the material basically. So how much will be the load at yield point? You can easily find that out. How? Because sigma y is equal to Py divided by area. Sigma y is known to you, area is known to you. You simply have to multiply them and get the value of Py or load at yield point for the rod. Okay, so it will be sigma y, which is 360 megapascal, multiplied by how much is the area? 200 centimeters square. So be careful about the units. I am converting this into meter square, right? So if you solve it, you are going to get 7.2 mega Newton. 7.2 mega Newton will be the load at yield point. And how much will be the deformation at the yield point? Now this is something that you need to again calculate by using the basics of the same expression. We know that del is equal to PL by EA, right? Which value of deformation we are interested in? To draw the load deformation curve, we need the values at yield point. How much is the load and how much is the deflection at yield point? So deflection at yield point is equal to load at yield point, right? And this area is obviously in the bottom, and load at yield point divided by area, what is that? Nothing but yield strength, stress at the yield point, which is P by A at yield point multiplied by L divided by E. Sigma y is known to us, E value is known to us, length was given to us in the question. If you look, the length was given to us as 500 mm, right? So all these values we know already. You just need to put them and solve them. Now since sigma and E, both of the units are similar, right? So you can convert gigapascal to megapascal by multiplying it with the 1000, and then megapascal will cancel. So E was in gigapascal, I multiplied that with 1000, and now sigma and E will have megapascal each, they will cancel out. Length I have kept in mm only, because if these two units cancel, the length unit will be the unit of combined expression. The length unit here is mm, so combined answer that I will get of deformation will be in mm. So when you solve this, you will get 1.5 mm. This will be the deformation at yield point. So if you draw that on load deformation curve, this is how it is going to look. This is the yield point. The load value is in mega Newton, the same that we calculated is in mega Newton, which is 7.2, right? And this is in mm. R I have written to show the deformation of the rod. So this is the required load deformation diagram for the rod. Now same thing we have to repeat for the tube. So for the tube also, the load at yield point, same concept, same formula, only instead of these values we are going to use these values and nothing else will change, right? So sigma y multiplied by A, you will get 4.5 mega Newton. For the deformation, you are going to use this expression, which is nothing but PL by EA. You put all the values from here and you are going to get 1.25 mm. Having known these two values at the yield point, we can draw the load deformation curve like this. The load 4.5 mega Newton and the deformation 1.25 mm. So up to this point, it's nothing new for you. These are some of the very basic expressions and basic concepts that we already know about. Now the question comes. Look at the question. The question was asking you to draw the diagram, which was the easy part. Now it is asking you to determine the net deformation when load of 11 mega Newton is gradually applied on this system. So you have this system where now you are gradually applying a load of 11 mega Newton, and now you tell that how much is going to be the deformation of this body. Try to solve this from this point, right? Try to solve it, and meanwhile I am continuing the discussion. So for your reference, whatever we have concluded so far, I have written here so that you know the values different values at yield point, both for both rod as well as for the tube. Now, if this was a regular question where there is a composite cross section or a composite bar to which you are applying a force P, what is the normal way? The normal way is to write the two equations, one for the load, other for the deformation, right? One equation will tell you that the load that you are applying will be distributed between them, right? So whatever load is felt by one plus felt by two, if you combine them, that will be equal to 11 meganewtons load. And then we will write another equation for the deflection, because it is a rigid plate. Whatever movement it does, same will be the deflection or deformation for both of them, since it is a rigid plate. And we solve it, we get the answer. This is how we usually solve. But this question is not going to get solved like that. Okay, let me tell you why. If you proceed with that method, what you will write? P1, or let's say PR in the rod, it is PR plus PT, P of tube, is equal to 11. And since it is a rigid plate at the end, the deflection or deformation for both of them will be same. So del will be same, which is equal to PL by EA. L is same for both of them. L and L will get cancelled. In this expression, EA for both of them are known to us. So PR and PT are only unknown. Here also PR and PT are only unknown. You may think two unknowns, we can solve it, but you cannot solve it. Why? The reason is that this expression you can apply. Del is equal to PL by EA. Where can you apply it? From where is this expression coming? This expression is coming from sigma is equal to E epsilon, which is coming from Hooke's law, which is only applicable in the elastic region. So this expression del is equal to PL by EA you can apply only when you are sure that the material for which I am applying this expression is within the elastic limit. If you are not sure about it, you cannot apply this expression for plastic region. In this case, are you sure that both of them are going to be in the elastic region? You are applying a load of 11 meganewton. One of them can take only 4.5 meganewton. After that, it will yield. Other can take only 7.2 meganewton. After that, it will yield. Can you guarantee that both of them will be in the elastic region? No, you cannot. At this point, you cannot. You cannot tell that whether one of them will be in the elastic region or both, or maybe both in the plastic region. You have to do the calculations to ensure that. And this is an important learning here. The question on load deflection or load deformation may not come in GATE, but this learning that you have got just now is very important for GATE. Whenever you are applying any of these expressions, always remember where the material or where the loading actually is. Is it in the elastic region or in the plastic region? Especially in the questions, especially if you get a question where load deformation curve or stress strain deformation curve is given to you. And clearly plastic region has been shown. In every such question, you have to pay attention and you have to notice whether the loading is in the elastic region or it entered into the plastic region. A very small thing to notice, but it will change the answer for you totally. So it's an important learning for you. Make sure to write it down in your numerical learning notes. So what have we concluded so far? That if we want to find out the individual values of forces maybe, or if you want to find out the net deflection also, you cannot do it. You cannot proceed using these two equations which we generally do, right? What we generally do from this, we find out the values of PR and PT, right? Using these two equations, and PR is known. Just put the value here, del R will be known, and del R and del T are same. So this is how we generally solve. But in this question, firstly we need to find out that what is the situation, whether both of them are in elastic or plastic, or maybe one of them is in elastic, other in the plastic, when a load of 11 meganewton is applied. So we need to draw the load deformation diagram, or we need to analyze the load and deformation for the load of 11 meganewton first, and then we will proceed with the question. So we tried to find out the deformation of this assembly by using the individual load deformation diagram or the individual values. but we were not able to do it, right? Because individually we are not aware whether which of them are in elastic or which of them are in plastic when you are applying 11 meganewton of force. So what we will do now, we will analyze it as an assembly. We are going to draw the combined load deformation diagram for this. That for this complete assembly, if we are applying 11 meganewton, in the combined load deformation diagram, where does this body stand? That we are going to see. Okay. Right now it may look slightly complex, but it is not. Just go with the flow and listen to me carefully. We have selected two specific values of deformation. Which two values? This one and this one. The deformation value at the yielding of tube and the deformation at the yielding of rod. 1.25 mm and 1.5 mm. And what we are going to see, that how much will be the value of load, how much will be the value of load for these values of deformation. Combined load I am talking about, combined load, okay, because it's a diagram for rod tube assembly, right? And then we will see that where the value of 11 is falling, whether that value of 11 is falling in the plastic region or in the elastic region, or maybe in a region where one of them is elastic, one of them is plastic. This is what the approach we are going to use. Now, in this case, if I want to know that how much will be the value of load when deformation will be 1.25 mm, how can I find that out? Listen to my question carefully. I want to find out the load at 1.25 mm deformation. Tell me at 1.25 mm, will both of them in elastic region or plastic region? Or maybe one in elastic, one in plastic. Have a look at this diagram. At 1.25 mm, this one is definitely in elastic region, right? 1.25 maybe somewhere here, which is in the elastic region. This is the elastic region, right? What about this? Here also it is at this yield point, means if this equation which I want to apply, the equation of elastic zone which we want to apply is applicable for this line, and this end and this end, both of them are a part of that line also. So which means that even though it is at the yield point, I can apply the analysis of elastic part because it is at the border. It is at the same elastic line at one end of it, right or not? So for 1.25 mm, this one is also, you can say, in the elastic zone, just entering or exiting the elastic zone, and this one is clearly inside the elastic zone, right or not? At 1.5 mm, what is going to happen? At 1.5 mm, this one is in the plastic zone, because at 1.25 it has reached here. After that, it is whatever force you are going to apply, it cannot sustain that. It can only take a load up to 4.5 meganewton. After that, it will just keep on flowing like a fluid, like water, because it's now plastic deformation, metal flow. So value of 1.5 will be in the plastic region only. So at 1.5 mm of deformation, combined deformation I am talking about, this one is plastic, this one has just entered the plastic. It is on the border of elastic and plastic, right? So on the basis of that, tell me what will be the value of load. What will be the value of load when the deformation will be 1.25 mm. Notice that whatever is the deformation of the rigid plate or of this assembly is same for both of them, right? So when both of them have deformed up to 1.25 mm, what will be the value of total load P at that instant? Now I can answer this question. How I can answer this question? How I can relate the individual force with the total force directly? Because I clearly know that at 1.25 mm, both of them are in the elastic zone or in the border of elastic zone, right or not? So I can easily apply my analysis and find out how much will be the total value of P when deformation, net deformation is 1.25 mm. If you look at the graph, you can rather answer it faster, even without using the expression of P1 plus P2 is equal to P and then writing del 1 is equal to del 2. Without doing all that also, quickly you can find out the answer using the load deformation diagram. At 1.25 mm, how much load will tube handle? Tell me. If a P, net P load you are applying, not 11, if a net P load you are applying at 1.25 mm, if it has deformed up to 1.25 mm, how much will be the load that tube is sustaining, that tube is getting loaded with? It is 4.5, right? When it has deformed, when you are deforming it and it just reached 1.25 mm deformation, the value of load at that point will be 4.5, right? What about the load here? So in this case, the load on the tube when the deformation is 1.25 is going to be 4.5. But what about the load on the rod? How much will be the load on the rod? 1.25 deformation is going to lie inside the elastic zone. Let's say here it is 1.25. You need to find out the load at that point. Suppose this is the load, which is X, right? Can you not find that value out? Easily you can find that value using the basics of geometry. Since it is a single line, both of them are the projections of the single line. X divided by 1.25, X divided by 1.25 is equal to 7.2 divided by 1.5. You can also call it the similar triangle property. This triangle and this triangle are similar. This is X, this is 1.25, this is 7.2, this is 1.5. So their ratios are going to be same. There are many ways in which you can proceed from there. And when you solve it, the value of X you will get as 6 mega Newton. So this rod, when deformed by 1.5 mm, is going to bear 6 mega Newton. This tube, when deformed by 1.25 mm, is going to bear 4.5 Newton. So individual loads, what they are going to carry, you have calculated that using only these diagrams, right? And only in the elastic region, by separately considering the elastic regions only up to 1.25 mm, because I know that up to 1.25 mm, both of them are in the elastic region. So I can easily find out the values. That is what I have done here. Only up to 1.25 mm, I have found out the individual values of force, and whatever is the individual value, P1 plus P2 has to be equal to P. It is the equilibrium condition. So what will be the total value of P when it has deformed by 1.25? P of rod plus P of tube. P of rod is equal to 6 mega Newton, P of tube is 4.5. So net value of P will be 6 plus 4.5 mega Newton. This is going to tell you 4.5 mega Newton, combined 10.5 mega Newton. This will tell you how much load will be acting, or how much load these two combined will be able to resist, will be able to withstand when both of them have deformed up to 1.5 mm, which is equal to 10.5 mega Newton. So in this diagram, if I want to write in this diagram, if I want to write and if I want to show, so at 1.25 mm, the combined load that they can resist is 10.5 mega Newton. This is what I have drawn now. What is the next checkpoint? The next checkpoint is 1.5 mm, right? Let us analyze things at 1.5 mm. What is going to happen when both of them, because they are deforming with the same speed, with the same value, both of them will reach the 1.5 mm deformation at the same time. This one, this rod, when it has reached 1.5 mm, it has reached the yield point where the value of load that it can resist is 7.2. So for 1.5 mm of deformation, it is resisting 7.2 mega Newton. But what about this one? What will be the value of load that it can resist at 1.5 mm? For any value of deformation equal or more than 1.25, it can resist only 4.5, because it has now started deforming perfectly plastically. So whatever be the value of deformation, 1.5 or 1500, the value of this load that it can resist is only 4.5, because this is the maximum load it can resist without yielding, right? So 4.5 is the value of load that it will be resisting at 1.5 mm, and this one will be resisting 7.2 at 1.5 mm. So when you add this and this, you get the total load that they will be resisting at 1.5 mm deformation. Please note what is different in this approach. In this approach, we are considering the plastic zone also, because we are not using the formulae, we are using the graph directly. Here we have found out the value of 4.5, right? Using the graph only. We did not use the Hooke's law and put the value 1.5 for tube. We cannot do that. We cannot put 1.5 deformation, because only in the Hooke's law's expression or in the del is equal to PL by EA for the tube, because tube is only elastically deforming up to 1.25. After that you cannot apply that. But if you used that expression, that will be a mistake. That's why we are using the graph directly. In the graph we can see that at 1.5 also this value is existing, right? So we have considered that in this analysis. We are considering the elastic zone also, the plastic zone also. This is the beauty of this approach, right? So at 1.5 mm, 7.2 plus 4.5, this is the net load that individually they will resist. So in total, from equilibrium equation, P is equal to P1 plus P2. This expression will be applied everywhere, whether elastic, whether plastic. It is the equation of equilibrium condition, which has got nothing to do with elastic or plastic. So if you add both of them, you will get 11.7, right? 4.5 plus 7.2. So at 1.5 mm, the load that they can resist is 11.7 mega Newton. Sorry, not mm, 11.7 mega Newton. Now there is one important point here, which you can actually analyze also, that the slope that they will be having after this point will change, right? The slope is not going to be same throughout, because up to this point, think what is happening. Up to 1.25, what is happening? Both of them are elastic. After 1.25, what is happening? After 1.25 mm, tube has entered into plastic, rod is still in the elastic, right? So now the deformation, how P and del will vary, is going to change slightly, because this part here from 1.25 to 5, the load deformation has changed. So the slope is not going to be having the same value. It will still be a linear slope, because this value is a constant. This value after 1.25 has become a constant. This value is still changing. So variation will be linear, but variation will not be at the same slope, because up to 1.25 both of them were changing. After 1.25 one stayed constant, other is changing. So rate will be linear, because change which is happening is still linear, but not both of them are changing. So slope is going to change like this. This I am drawing for the combined assembly, not for a specific body. This is something that you need to realize about P, del or load deformation diagram. It is not like sigma, epsilon or stress strain diagram, which is drawn generally to analyze a material, right? For this combined assembly, it will not make a lot of sense to have a sigma epsilon diagram or stress strain diagram. But for such an assembly, it will make a lot of sense to have a P del diagram. And this is what you need to understand, that although in majority of the discussion we talk about stress strain diagram, which is true if you want to compare two different materials, if you want to understand the material properties, material behavior. But if you want to analyze the component's behavior, this is a specific component under a specific loading, these diagrams are more suited for practical application. Okay, and since they are very much in the GATE syllabus, don't think that they are not in the GATE syllabus, they are very much in the GATE syllabus. You must know how to draw them. Okay, so basic discussion about them we have already done, so it's not that you are first time hearing about P del diagram. Okay, this value of P is going to be 11.7 mega Newton. And now let us have a look at the question. The question was asking us that determine the net deformation when a load of 11 mega Newton is gradually applied. When you are applying a total load P of 11 mega Newton, it is the total load P, right? Tell me where will it lie? This is, let's say, point A, this is point B, this is point C. Clearly it is going to lie between point B and between point B and C, because 11 will come somewhere here, right, between 10.5 and 11.7. If it is lying somewhere here, what does it tell you? It clearly tells you that this one is in the plastic zone, rod is in the elastic zone, right? This region between B to C is the same region when the tube, I think this was the tube, right? Yeah, tube entered the plastic region, rod entered the elastic region. So the approach that you were using of equating the del using PL by EA, that you cannot do for which of them? That you cannot do for tube, because tube has entered the plastic region. So from this discussion we can conclude that when a load of 11 meganewton is acting, it is lying somewhere here, the load is coming somewhere here. So the deformation is coming somewhere between 1.25 and 5, right? Which clearly means that if deflection or deformation is between 1.25 to 5, this one is in the elastic region or at just the border of elastic region, but this one is in the plastic region, because any value which is higher than 1.25 will enter into the plastic region, and it is a value at 11 meganewton. At 11 meganewton, it is a value which is higher than 1.25, right? So if you want to find out the value of deflection, because deflection will be same for both of them, they are part of the same assembly. So if you want to use the value del is equal to PL by EA, you want to use this expression, you can use this for the rod but not for the tube, because this is no longer in the elastic region, right? Now if you want to use this expression of del is equal to PL by EA for the rod, this is going to be the expression. P value will be specifically the load which is distributed on or which is coming on the rod, right? L value is known, E value, A value is known, but still PR individually is not known to you. You know that total load acting is 11, but how much is the load that is acting on the rod? Now you can answer that. How? We know that 11 is going to fall in the deformation 1.25 to 5, and when it is from 1.25 to 5, the tube is in the plastic, and if tube is in the plastic, it can only resist a load of 4.5. It cannot resist a load more than that. If tube has deformed more than 1.25, its work, its contribution cannot be increased. It can only sustain 4.5. Whatever extra load you are applying after that, it will say that I cannot carry, I am yielding. You take the load. So whatever load is coming after 1.25 mm has to be borne by the other part. So we know that the deflection or deformation of the assembly will be same whether it is rod or tube. Both of them are having the same deflection, same deformation. But to find out the deformation using expression of PL by EA, we can use only the one which is in the elastic region, which is the rod, right? So this expression we can use, del is same for both, and del of rod is PL by EA. P of rod, the load which is shared by the rod, will be equal to total load which is acting, which is 11 meganewton, minus the load, maximum load which can be shared by the other component, which is tube. Tube can only share up to 4.5, because after that it will yield. So rest of the load will have to be shared by the rod. So that value is going to come here. P is 11 minus 4.5. Then you just put the value, length is known to us, the Young's modulus is known to us, area is given to us, everything is given. Then you just have to put the values, taking care of the sign, and then solve it. You will get the answer as 1.354 mm. So this question, although it is an easy question, doable question, it's not a difficult one, but there is a conceptual mistake possible that you may assume automatically that they are going to be in the elastic region. That is a wrong assumption. And since I wanted to discuss this question from the load deformation point of view to make you more comfortable in the load deformation diagram also, so I used the diagram approach. You can do it without using the diagram approach also. There is no harm, you will reach the answer, but this way will make you more confident and comfortable with the load deformation diagrams. The question is not over yet. This is the first part of the question. The second part is that if you now unload the 11 meganewton force to 0, what will be the final and permanent deformation in the body when the load is totally removed? So from this point, you are going to now unload this particular load up to 0, and then you have to tell what is going to happen in the load deformation curve, how is it going to move, and ultimately decide the answer. Let us discuss that in the separate question.